Welcome back to Axiox. There are moments in the history of our species where the curtain of the cosmos is pulled back, not gently, but with a violence that shatters our preconceived notions of isolation. For thousands of years, we looked up at the night sky and saw a clockwork mechanism, a predictable, orderly, and closed system. We believed that everything moving through the heavens, every wandering star, every fiery comet, every silent asteroid, was kin. We believed they were all born from the same primordial cloud of gas and dust that coalesced to form our sun some 4.6 billion years ago. We believed that the solar system was an island, vast and lonely, separated from the nearest shores of other stars by an ocean of void so deep and so dark that nothing could drift across it. We were wrong. The ocean is not empty. It is full of driftwood, and right now, one of those pieces of driftwood, a mountainous fragment of an alien world, a traveler from a star system that may have died before humanity even learned to walk upright, is tearing through our neighborhood. We are not merely covering a news update today. We are documenting a collision between human observation and interstellar reality. We are tracking the object designated 3I Atlas, the third confirmed visitor from the deep interstellar medium. But unlike its predecessors, unlike the ghostly Oumuamua or the typical Borisov, 3I Atlas has arrived at a moment of convergence. It has arrived just as our own star, the Sun, is waking up into a violent solar maximum. It has arrived just as our observational technology is reaching a peak of sensitivity. And it has arrived just as the institutions tasked with watching the sky, specifically NASA, have entered a period of cryptic silence that is only now, in less than 40 hours, about to break. We have a situation developing in the inner solar system that is unprecedented in the history of modern astrophysics. We have an object of unknown size and composition, exhibiting anomalous behavior, that is currently in the crosshairs of a massive solar eruption. This is not hyperbole. This is orbital mechanics and plasma physics playing out in real time. Today, we are going to deconstruct the impending NASA data release, the physics of the inbound coronal mass ejection, and the profound implications of what we are witnessing. We are going to strip away the noise of the internet rumor mill and replace it with the hard signal of geophysics, electromagnetism, and high-energy astronomy. But to understand the gravity of this week, to understand why a scheduled live stream on a Wednesday in November is potentially a history book event, we must first understand the context. We have to understand the silence that preceded it. The arrival of objects from beyond our solar system was, for the longest time, a theoretical exercise. It was a mathematical probability, a line in a paper, a what if. We knew, statistically, that the formation of planetary systems is a messy business. We know from our own solar system's history that the migration of giant planets like Jupiter and Saturn acted like gravitational snowplows, ejecting trillions of tons of rock and ice into the void. It stands to reason that every other star system in the Milky Way does the same. The galaxy should be teeming with these ejected orphans, these floating time capsules. But until 2017, we had seen exactly zero. Then came Oumuamua. One-eye Oumuamua, the scout. It dropped into our system like a dagger, moving at a speed and on a trajectory that defied the sun's gravity. It was red, it was tumbling, It was elongated like a cigar, and it was silent. It showed no tail, no coma, yet it accelerated as if it were being pushed by something. It broke our models. It forced us to invent new categories. It forced us to ask if we were looking at a rock or something else. Then came 2I Borisov in 2019. If Oumuamua was the anomaly, Borisov was the comfort. It looked like a comet. It acted like a comet. It had a tail. It outgassed water and cyanide. It told us, yes, other star systems make comets just like ours. It was a standard sample, a baseline. And now we have 3I Atlas, the third, the tiebreaker. But 3I Atlas is refusing to fit into either box. It is not the inert rock that Oumuamua was, nor is it the standard dirty snowball that Borisov was. It is something in between, and something more. It is an object that was initially classified as a comet, then suspected to be an asteroid, and is now displaying a level of activity that seems physically impossible for its estimated size. It has developed a massive, diffuse coma, a cloud of gas and dust that, at one point, was estimated to be nearly half the diameter of the Sun. Think about that scale. A tiny nucleus, perhaps only a few kilometers wide, generating a cloud of material nearly 1,000,000 kilometers across. It has developed tails, not just one, but complex structures, including a sunward-facing jet, or anti-tail, that defies simple explanation. And it has done all of this while enduring the intense radiation environment of the inner solar system. This brings us to the immediate news, the first pillar of our deep dive today. NASA has broken its silence. For weeks, the astronomical community has been in a holding pattern. We knew that the Mars Reconnaissance Orbiter, or MRO, a veteran spacecraft orbiting the red planet, had been slewed to point its high-resolution camera at 3I Atlas on October 3rd. We knew the data was taken. We knew the photons had hit the sensor. We knew the bits had been beamed back through the deep space network. But we saw nothing. The public release channels were quiet. The image repositories were not updated. In an age of instant gratification, where we expect live feeds from the surface of the moon, this delay created a vacuum. And in a vacuum, speculation expands to fill the void. Theories ran wild. Was the object artificial? Was it disintegrating? Was there a threat? The reality, as is often the case in science, is likely bureaucratic and technical, but the timing of the release is undeniably dramatic. NASA has announced a special live stream event scheduled for this Wednesday, November 19th, at 12 p.m. Pacific Time. They are not just dumping the images on a server, they are building an event around them. This suggests confidence. It suggests they have something worth explaining. The choice of November 19th is significant because it coincides with a specific planetary geometry, a moment of alignment that historically and mathematically represents a window of clarity. but more practically, it represents the end of the analysis period. The scientists have had their time with the data. Now the world gets to see. Why does this MRO image matter? Why is everyone, from the professional astrophysicist to the backyard observer, counting down the hours? It is not just about seeing a pretty picture. 3i Atlas is too small and too far away, even for the MRO, to look like a detailed world with mountains and craters. We aren't going to see a surface map. What we are looking for, what we are desperate for, is a single number, the diameter. Currently, we are flying blind regarding the mass of this object. The Hubble Space Telescope provided early estimates, suggesting a nucleus size of up to 2.8 kilometers. But other ground-based observations, struggling with the glare of the coma, have offered upper limits as high as 50 kilometers. In astrophysics, a difference between 2.8 kilometers and 50 kilometers is not a margin of error. It is a chasm of ignorance. If the object is 50 kilometers wide, its massive coma is expected behavior. It's a giant object releasing a lot of gas. But if the object is truly small, if it is close to that 2.8 kilometer Hubble estimate, or even smaller, then the massive coma becomes a paradox. How can such a tiny rock release so much material so fast? Is it evaporating entirely? Is it not a solid rock at all, but a fluffy aggregate of dust and ice, less dense than cotton candy, held together by van der Waals forces and hope? The HiRISE camera on the MRO is the most powerful camera we have ever sent to another planet. It is capable of resolving objects the size of a dinner table on the surface of Mars from orbit. While observing a comet millions of kilometers away is a different optical challenge, the MRO has one distinct advantage over Earth: perspective. On October 3rd, when the image was taken, the viewing angle from Mars was different than from Earth. The phase angle, the angle between the Sun, the object, and the observer, allowed the MRO to see the comet illuminated in a way that might allow us to peer through the coma and isolate the point source of the nucleus. If NASA reveals on Wednesday that the nucleus is indeed tiny, we are looking at a new class of interstellar object, a hypervolatile fragment that might be pure ice, or perhaps something even more exotic, like a hydrogen iceberg, though that theory has been contested. But the NASA release is only half of the story. While we wait for archival data from October, the solar system is moving forward in real time. We are not just watching a static object. We are watching a dynamic interaction. The sun is the dominant force in our system, a roaring sphere of plasma governed by twisting magnetic fields. It breathes, it pulses, and occasionally it screams. And right now, the sun is screaming in the direction of 3i Atlas. This brings us to the second pillar of our analysis, the inbound coronal mass ejection, or CME. Today, November 17th, space weather monitors lit up. An active sunspot group, a knot of magnetic complexity on the surface of the sun, destabilized. Magnetic field lines that had been twisted and stretched to their breaking point suddenly snapped, a process known as magnetic reconnection. This process converts magnetic potential energy into kinetic energy and heat, blasting 1 billion tons of superheated plasma out into the void. This is a CME. It is a shotgun blast of particles, protons, electrons, heavy ions, traveling at millions of kilometers per hour. We have been tracking this sunspot group for weeks. It is the same group that rotated across the Earth-facing disk recently, peppering our planet with X-class flares and causing geomagnetic storms that pushed auroras down to the mid-latitudes. It has now rotated off the western limb of the Sun, moving to the far side. From Earth's perspective, it is gone. But space is 3D. Just because it is not pointing at Earth does not mean it is firing into emptiness. We must look at the ecliptic plane, the imaginary flat disk upon which the planets orbit. Using data from the Solar Dynamics Observatory, SDO, and the chronograph images from SOHO, the Solar and Heliospheric Observatory, we can reconstruct the firing solution of this blast. The explosion occurred on the limb. It was not directed at Earth, but when we plot the position of 3I Atlas, we see a chilling alignment. 3I Atlas is currently plunging through the inner solar system, moving on its hyperbolic trajectory. It is positioned slightly above the ecliptic plane. The CME that launched today also launched on a trajectory slightly inclined above the ecliptic. It is not an Earth-directed event. It is an Atlas-directed event. Space weather prediction is difficult. It is fluid dynamics on a stellar scale. But the Enlil spiral models, the sophisticated computer simulations used by NOAA and NASA to track solar wind, show a direct intersection. The plasma cloud is projected to sweep over the position of 3I Atlas on or around November 22nd at 12 Universal Time. This is not a gentle breeze. This is a hammer blow. And 3I Atlas is not the same object it was a month ago. A month ago, it was quieter, more compact. Now, post-perihelion, it is fully awake. It has a developed ion tail, a stream of charged gas pushed by the solar wind. It has a developed dust tail. It has a massive surface area of interaction. When a CME hits a comet, it is a clash of magnetospheres. The comet has its own induced magnetosphere, created by the ionization of its atmosphere. The CME carries its own magnetic field, frozen into the plasma. When these two magnetic environments collide, we expect violence. We expect a sudden compression of the comet's magnetosphere. We expect the brightness of the comet to potentially flare as the density of the surrounding plasma spikes. But most dramatically, we look for a tail disconnection event, or TDE. This is where the pressure of the solar wind and the reconnection of magnetic field lines literally snips the ion tail off the comet. The tail detaches and drifts away downstream, a ghost of the comet left behind, while the nucleus immediately begins to grow a new one. We observed this with Comet Encke in 2007. We observed this with Comet 67P during the Rosetta mission. And now we have a front row seat to see if the Sun will decapitate an interstellar visitor. This is a rare opportunity to stress test the object. By seeing how it reacts to a CME, we learn about its density, its magnetic susceptibility, and the rate of its ion production. We are essentially poking it with a stick to see what it's made of. So, the stage is set. On one hand, we have the retrospective clarity of the impending NASA data dump, which will hopefully tell us what this object is physically. On the other hand, we have the prospective drama of the solar impact, which will tell us how this object behaves electromagnetically. In the next section of this deep dive, we are going to pull apart the history of the Interstellar 1 designation. To understand why 3I is so important, we have to look back at 1I and 2I. We have to look at the statistical impossibility of Oumuamua and the chaotic normality of Borisov. We have to understand that we are currently building a catalog of alien matter, one sample at a time. And we have to ask the uncomfortable question, why now? Why 3 in less than a decade after centuries of silence? Is our technology just getting better, or is the galaxy getting more crowded? Let's descend into the history of the designation. To understand the violence currently hurtling toward 3I Atlas, we must strip away the comforting image of the sun as a static yellow ball and see it for what it truly is, a magnetic beast driven by a chaotic internal engine known as the solar dynamo. This engine is not powered by combustion, but by the shearing of plasma, a state of matter so energetic that electrons are stripped from their atomic nuclei, creating a soup of charged particles that conducts electricity better than copper wire. Because the sun is not a solid body, it does not rotate uniformly. The equator spins faster than the poles, completing a rotation in about 25 days compared to the poles' 35 days. This differential rotation drags the sun's magnetic field lines, which are frozen into the plasma, stretching and winding them around the star like rubber bands on a spinning top. Over time, this tension builds until the magnetic fields become so twisted and buoyant that they punch through the surface, creating the dark, cooler islands of magnetism we call sunspots, which are effectively the muzzle of the gun now pointed at our interstellar visitor. The explosion that occurred on November 17th was the result of a catastrophic snapping of these twisted magnetic lines, a phenomenon geophysicists call magnetic reconnection. When two opposing magnetic field lines are forced together in the chaotic environment above a sunspot, they can suddenly break and reconnect in a lower energy configuration, releasing the stored magnetic potential energy in a fraction of a second. This release is explosive, heating the local plasma to tens of millions of degrees and accelerating particles to near relativistic speeds. This is the flash of a solar flare. But the flare is just the muzzle flash. The bullet is the Coronal Mass Ejection, or CME. In this event, 1 billion tons of magnetized plasma, a flux rope of twisted magnetic fields and superheated gas, was hurled into space. Unlike the constant, gentle stream of the solar wind, a CME is a shock wave, a coherent structure that acts like a supersonic snowplow, scooping up the ambient medium and driving a wall of compressed particles ahead of it. This specific CME is now propagating through the inner solar system, and its interaction with 3I Atlas will be governed not by gravity, but by magnetohydrodynamics, or MHD, the study of the magnetic properties of electrically conducting fluids. As the shock front races outward, It expands, but it retains its punch. Space weather models, specifically the Enlil spirals used by NOAA and NASA, predict the arrival of this shock at the comet's location around November 22nd. The timing is critical because the impact is not merely a physical collision of particles, it is a collision of magnetospheres. 3I Atlas, now active and outgassing, has created its own protective bubble, an induced magnetosphere formed where the pressure of its cometary ions balances the pressure of the solar wind. This boundary, called the ionopause, effectively deflects the solar wind around the nucleus, creating a cavity in the flow. When the CME slams into this cavity, the pressure balance will be instantly and violently overturned. The dynamic pressure of the solar wind will jump by orders of magnitude, crushing the comet's magnetosphere inward toward the nucleus. We saw exactly this scenario play out with the Rosetta spacecraft at Comet 67P, where a CME impact compressed the plasma environment so severely that the magnetic field strength measured by the probe jumped from a quiet 30 nanotesla to a chaotic 300 nanotesla. This compression forces the cometary ions into a smaller volume, increasing their density and potentially causing the entire coma to brighten. Significantly, a plasma flare that might be visible to Earth-based observers if the geometry allows. But the most dramatic potential consequence of this impact is a tail disconnection event. The ion tail of a comet is not a trail of smoke. It is a stream of charged particles guided by the interplanetary magnetic field, or IMF, which is carried by the solar wind. The ion tail is essentially frozen onto these field lines. A CME carries with it a discontinuity in the magnetic field, a sudden shift in the direction or polarity of the magnetism. When this magnetic discontinuity sweeps over the comet, the field lines connecting the tail to the head can be severed and reconnected to the new field lines of the CME. The visual result is a decapitation. The existing ion tail is pinched off and swept away downstream by the solar wind, drifting free into the void, while the nucleus immediately begins to sprout a new tail. Observing such an event on 3I Atlas would be the ultimate confirmation of its plasma-dominated nature, proving that this interstellar visitor is obeying the same laws of electrodynamics as our local comets, effectively passing a stress test designed by the Sun itself. This potential violence brings us back to the object's anomalous features, specifically the anti-tail and stable jets that have fueled so much speculation. In the absence of understanding the plasma environment, these features look impossible. How can a rotating, tumbling object maintain a steady beam of material? The answer lies in the invisible architecture of the coma. The electric and magnetic fields surrounding the nucleus act as a lens, a guide that channels charged dust and gas along specific field lines regardless of the nucleus's rotation. The anti-tail, often cited as a mystery, is an optical and physical phenomenon where large, heavy dust particles are left behind in the comet's orbital plane. When we view the object from Earth as it crosses the plane of the ecliptic, we see this disk of dust edge on, appearing as a spike pointing toward the Sun. For 3I Atlas, this effect is amplified by anisotropic illumination, where the sunward side is heated more intensely, allowing larger, heavier ice grains to survive longer and travel further in that direction, extending the snow line of the comet toward the star and creating the illusion of a sunward jet.
This rigorous physical explanation dismantles the black swan hypothesis, the idea that 3I Atlas is a technological artifact or an alien craft. The black swan theory relies on the premise that the object's behavior cannot be explained by natural laws, necessitating an artificial origin. However, when we apply the full weight of cometary physics, accounting for the rocket effect of outgassing, the electromagnetic channeling of jets, and the optical geometry of dust trails, every single anomaly dissolves into a predictable, albeit extreme, natural phenomenon. Oumuamua was a rock that outgassed.
Invisible hydrogen. 3I Atlas is a volatile snowball processing intense solar radiation. The desire to find a spaceship is human, but the data points to a piece of a dead solar system, a fragment of a planetary disk that was torn apart by gravity and flung into the dark, only to be relit by our sun for a brief, brilliant moment of analysis. As we await the NASA data release on Wednesday, we are looking for the final piece of this puzzle, the nucleus size. If the high-resolution imagery from the Mars Reconnaissance Orbiter reveals a tiny, sub-kilometer object, it will confirm that 3I Atlas is a hyperactive body, likely a fluffy aggregate of low-density ices that is disintegrating rapidly. If it reveals a larger body, we will have to rewrite our models of cometary outgassing efficiency. Either way, the silence is breaking. The data is coming down from the Deep Space Network, the CME is rushing out from the sun, and humanity is watching. We are not just observing a dot in the sky, we are witnessing a masterclass in cosmic interaction, a collision of history, physics, and probability that reminds us that the universe is not a static painting, but a dynamic, dangerous, and deeply connected machine. To understand the sheer magnitude of the event currently unfolding across the inner solar system, we must abandon the terrestrial intuition that governs our daily lives. On Earth, if you fire a cannon, the projectile moves in a ballistic arc, governed by gravity and air resistance. In the solar system, however, when the star at the center of our lives fires a weapons, the rules of engagement are dictated by a different, far more violent set of laws: magnetohydrodynamics. The coronal mass ejection that erupted on November 17th is not merely a cloud of hot gas. It is a magnetized structure, a distinct physical entity with a front, a core, and a trailing wake, moving through a background medium that is itself electrically charged. To appreciate why the upcoming collision with 3I Atlas is such a scientifically rich moment, we have to dissect the anatomy of this solar storm with a level of granularity that goes beyond the headlines. The genesis of this blast lies in the concept of magnetic reconnection, a process that sounds abstract but is responsible for the most energetic events in our solar system. Imagine the magnetic field lines above a sunspot group as twisted rubber bands, storing immense potential energy generated by the sun's differential rotation. When these lines are forced together by the churning plasma of the photosphere, they snap. In a fraction of a second, the magnetic topology changes, and that stored energy is converted instantly into kinetic energy and thermal heat. This is the trigger. The material that is ejected, billions of tons of protons, electrons, and heavier ions like iron and oxygen, is accelerated to speeds that defy comprehension, often exceeding 2,000 kilometers per second. But unlike a bullet, which is disconnected from the gun once fired, a CME remains magnetically tethered to the sun during its initial expansion, stretching out a flux rope of magnetic fields that defines its internal structure. As this structure punches through the sun's outer atmosphere, the corona, it creates a shock front. This is where the physics becomes critical for 3I Atlas. The space between the planets is not empty. It is filled with the solar wind, a tenuous stream of particles constantly flowing outward. When the CME moves faster than the Alvan speed, the speed at which magnetic waves can travel through that background plasma, it creates a sonic boom, a shock wave that piles up material ahead of it. This shock front is a wall of compressed plasma and amplified magnetic fields, and it is this wall that is currently racing towards the interstellar intercept. The density of particles in this wall can be 10 to 50 times higher than the ambient solar wind, and the magnetic field strength can spike dramatically. It is not just a gust of wind, it is a solid hammer blow of pressure. Tracking this hammer blow requires us to understand the geometry of the battlefield. Space is three-dimensional, but our maps are often two-dimensional, leading to a false sense of simplicity. The solar wind does not radiate outward in straight lines like light from a bulb. Because the sun rotates, the magnetic field lines spiral outward, creating a shape known as the Parker spiral. It looks like the water spraying from a rotating garden sprinkler. A CME, while launching radially, must propagate through this spiraling structure. The Enlil prediction models, named after the Sumerian god of the wind, are complex hydrodynamic simulations that calculate how this blast wave deforms as it travels. They account for the drag of the background solar wind and the expansion of the cloud. The specific solution for the November 17th event shows a trajectory that is slightly inclined. This is the key detail. 3I Atlas is not sitting perfectly on the ecliptic plane, the flat disk where Earth and the other planets orbit. It is currently plunging through the system on a hyperbolic trajectory that takes it slightly above this plane. The fact that the active sunspot region was also positioned at a high latitude means the barrel of the gun was elevated to match the target. It is a rare geometric convergence, a sniper shot across 150 million kilometers of void. This leads us to the moment of impact, slated for November 22nd. When that shock front arrives at 3I Atlas, we are going to witness a collision between two fundamentally different regimes of matter. For decades, the popular image of a comet was the dirty snowball, a sublimating lump of ice where physics was dominated by thermodynamics. Heat melts ice, gas expands, dust flies off. Simple. But 3I Atlas is forcing us to adopt the electric comet framework. In this model, the comet is not just a melting rock, it is a plasma obstacle. As 3I Atlas outgasses, it creates a cloud of neutrals, uncharged atoms. But as soon as these atoms are hit by solar UV radiation, they lose an electron and become ions. This creates a conductive bubble around the nucleus. When the solar wind flows past this bubble, it cannot penetrate it directly. Instead, it creates a boundary layer called the ionopause and a bow shock upstream, similar to the wave in front of a ship. The region between the bow shock and the ionopause is a chaotic zone of turbulence. Under normal conditions, this system is in equilibrium. But when the CME arrives, that equilibrium is shattered. The external pressure will jump instantly. The bow shock will be pushed inward, crushing the cometary magnetosphere down toward the nucleus. This compression increases the local plasma density, which can lead to a sudden brightening of the coma, not because more ice is melting, but because the existing gas is being squeezed and energized. Furthermore, we must consider the anomalous tails of 3I Atlas through this electromagnetic lens. The stable jets and the sunward-facing anti-tail have perplexed those using standard gravity-based models. However, if we view the coma as a dusty plasma environment, the mystery resolves. Dust grains in space are not neutral. They collect electric charges from the surrounding plasma. Once charged, they are no longer subject only to gravity and radiation pressure. They are subject to the Lorentz force. They feel the pull of electric and magnetic fields. The jets we see may not be fountains erupting from the surface, but rather current sheets, specific channels in the electromagnetic environment of the coma where charged dust is being funneled and focused. The upcoming CME impact will act as a stress test for this theory. If the jets are hydrodynamic, gas pressure, they should just waver slightly in the wind. If they are electrodynamic, plasma currents, the arrival of the massive magnetic flux rope of the CME could cause them to twist, snap, or realign violently. We might see the entire morphology of the comet distort in real time as the external magnetic field direction flips. This interaction also has profound implications for the chemistry we are about to analyze from the NASA data dump. The surface of 3I Atlas has been bombarded by cosmic rays for millions of years in the interstellar medium, creating a dark, carbon-rich crust. The arrival of the CME provides a burst of sputtering, a process where heavy ions from the solar wind slam into the surface and knock atoms loose, like billiard balls. This could release chemical species that are typically locked deep in the crust, momentarily enriching the coma with heavy, non-volatile elements. If we have spectrographs pointed at the object during the impact window, we might see a sudden spike in iron, magnesium, or silicates in the gas cloud, giving us a direct read on the elemental composition of the object's surface without ever landing a probe.
The stakes of this observation are incredibly high because 3I Atlas represents a sample of a failed solar system. The material we are looking at, the ices, the silicates, the organic tars, was likely formed in the protoplanetary disk of another star. It is the construction debris from a building project that happened light years away. By studying how it reacts to our sun, we are essentially doing comparative planetology. Does the water ice in 3I Atlas sublimate at the same rate as solar system water ice? Does the dust charge up the same way? Or is the material fundamentally different, perhaps more porous, or composed of different isotopic ratios? The violence of the CME acts as a probe. It strips away the outer layers and forces the object to reveal its internal structure. A tail disconnection event, where the ion tail is ripped away, would provide a visual tracer of the solar wind's magnetic topology, but it would also reveal the mass loading rate of the comet, how fast it is dumping tons of material into the tail to rebuild it. As we count down to the release of the high-resolution images from the Mars Reconnaissance Orbiter, we must keep this dynamic context in mind. The static image we will see on Wednesday is a snapshot from the past, taken on October 3rd. It will give us the baseline, the size of the nucleus, the shape of the coma in a quiet state. But the reality of today, and the reality of November 22nd, is a movie, not a photo. We are watching a live experiment. The data from the MRO will constrain the physical parameters: diameter, albedo, rotation rate. We will then plug those hard numbers into our magnetohydrodynamic simulations of the CME impact
to see if the math lines up. If the MRO tells us the nucleus is tiny, say 500 meters, then the massive coma and robust resistance to the solar wind implies an incredibly high charge density, or a surface that is evaporating explosively. If the nucleus is large, say 20 kilometers, then the activity is surprisingly low, suggesting a thick, insulating crust. The convergence of these two events, the data release and the solar impact, creates a unique moment in scientific history. We are not just cataloging a rock, we are characterizing an active alien world as it fights to survive the hostile environment of our star. The silence from NASA was the deep breath before the plunge. Now we dive. We dive into the pixels of the HiRISE camera, and we dive into the plasma shockwave of the CME. And at the bottom of that dive, we hope to find the truth about where we come from and what else is out there in the dark. To grapple with the reality of 3I Atlas, we must descend from the fiery spectacle of the solar atmosphere down to the cold, hard mathematics of the object itself. The central question that the impending NASA release aims to answer is deceptively simple. How big is it? In our daily lives, size is obvious. In astronomy, size is a ghost. We cannot take a ruler to an object
that is 150 million kilometers away. We can only measure the amount of light it reflects, a value known as its absolute magnitude. But here lies the trap, the fundamental ambiguity that has plagued the study of this visitor since its discovery. The brightness of an object is determined by two variables, its physical size and its reflectivity, or albedo. A small ball of polished mirror reflects the same amount of light as a massive ball of coal. We know how bright 3I Atlas is. We have measured the photons impacting our CCD sensors with high precision, but we do not know if it is a mirror or a lump of coal. This is the albedo ambiguity. Most comets in our solar system are incredibly dark, darker than asphalt, with an albedo of about 0.04, reflecting only 4% of the sunlight that hits them. If 3I Atlas is a typical dark comet, then to account for its observed brightness, it must be relatively large, perhaps the 20 to 50 kilometers suggested by some ground-based observations. However, if 3I Atlas is fresh, pristine ice, a shard of a frozen ocean that has never been baked by a star before, its albedo could be 0.6 or higher. In that case, it could be a tiny fragment, perhaps only 1 or 2 kilometers across, dazzling us with its brilliance. The Hubble Space Telescope's estimate of a sub-3 kilometer nucleus assumes a certain albedo, but without the spatial resolution to see the disk of the object, it remains an educated guess. The Mars Reconnaissance Orbiter data is our best hope of breaking this degeneracy, because observing from a different phase angle helps constrain how the object scatters light, allowing us to triangulate the true surface properties. Why does this matter? Because the size dictates the density, and the density dictates the origin. If 3I Atlas is large, 50 kilometers, but is being pushed around by non-gravitational forces as strongly as we observe, it implies the object is effectively a hollow shell or a fractal aggregate, a construct so porous it would float on air. This leads us to the fairy castle structure hypothesis. In the freezing vacuum of a protoplanetary disk, dust grains collide and stick together gently, forming spindly, branching structures that look like coral. If 3I Atlas is a pristine chunk of this material, it might have a bulk density lower than styrofoam.
It would be a rubble pile of the highest order, held together not by gravity, but by van der Waals forces, the weak electrostatic attraction between molecules. A collision with a CME in this scenario wouldn't just strip the tail, it could mechanically disintegrate the nucleus, shattering the fragile lattice structure and turning the comet into a cloud of expanding dust. This is why the stress test of the solar storm is so critical. It measures the structural integrity of alien matter. But beyond the physical body, there is the undeniable proof of its alien nature written into its movement. We must pivot now to the mechanics of the void, Module 3 of our
investigation, to understand the irrefutable evidence that 3I/Atlas is not from here. The definition of home in celestial mechanics is energy. An object is home if it is gravitationally bound to the sun. Mathematically, this means its total orbital energy is negative. It doesn't have enough speed to escape the gravity well. 3I/Atlas, however, has positive orbital energy. It fell into our system with a hyperbolic excess velocity of several kilometers per second. This is the speed it possessed when it was infinitely far away, before the sun's gravity even began to accelerate it. To visualize this, imagine a skateboarder dropping into a half-pipe. If they start at the rim, they roll down, pick up speed, and roll up the other side to the same height. They are bound to the pipe. But 3I/Atlas didn't start at the rim. It started way above the ramp, diving in with a massive initial boost. It screamed down the gravity well, whipped around the sun, and is now shooting back out with enough speed to leave the half-pipe forever. This trajectory, defined by an eccentricity significantly greater than 1, is the mathematical fingerprint of an interstellar origin. It is impossible for a solar system object to naturally acquire this orbit through standard planetary interactions. It had to come from the outside. The vector of this incoming velocity tells us even more. By rewinding the clock and subtracting the motion of the sun and the Earth, we can determine the object's velocity relative to the local standard of rest, the average motion of stars in our neighborhood of the Milky Way. 3I/Atlas's velocity vector does not align with the solar apex, the direction the sun is moving. Instead, it seems to originate from a generic background population of galactic stars. This kinematic analysis suggests that 3I/Atlas has been drifting for a very, very long time. It is not a recent ejecta from a nearby star like Alpha Centauri. It is likely a galactic wanderer, an object that has crossed thousands of light years, perhaps passing through multiple star systems before stumbling into ours. It is a statistical traveler, a sample of the galactic background. This profound isolation explains the excitement around the I designation. We are not just looking at a rock, we are looking at a time capsule from a different epoch of galactic history. If the galaxy is 13 billion years old, 3I/Atlas could be 8 billion years old, or 2 billion. Its composition, the ratio of carbon to oxygen, the presence of complex organics, is a snapshot of the chemical conditions in a star formation region that may no longer exist. When we analyze the spectra in the coming weeks, looking for the emission lines of cyanogen or diatomic carbon, we are essentially reading the recipe card of a dead star. If we find that 3I/Atlas is carbon chain depleted, like our own comets, it implies a universality to the chemistry of planet formation. If we find it is radically different, rich in exotic species or possessing isotopic ratios that clash with solar values, it proves that the recipe for worlds varies wildly across the Milky Way. The convergence of the high-resolution imaging and the orbital backtracking allows us to build a profile of the suspect. We have a small, potentially fluffy, hyperactive, chemically complex traveler that has survived a journey of eons only to run the gauntlet of our sun's solar maximum. The silence from NASA, the delay in the data, is likely the result of scientists grappling with contradictions in this profile. How can something so old be so active? How can something so small produce such a massive coma? The data released on Wednesday will likely resolve one variable, size, but in doing so, it may make the others more confusing. If the nucleus is tiny, the mass loss rate is impossibly high. If the nucleus is large, the darkness is impossibly deep. As we stare at the screen waiting for the feed to go live, and as we watch the space weather monitors for the impact of the CME, we are witnessing the scientific method in its rawest form. Theory collides with observation, models collide with reality, and a comet collides with a solar storm. The interstellar awakening is not just about discovering these objects. It is about realizing that our solar system is porous, a permeable membrane in a vast, interconnected ocean of material. 3I Atlas is the wake-up call, the bell tolling in the night to tell us that we are not alone in the dark, and that the dark is full of debris. The next 72 hours will determine whether that debris is a Rosetta Stone for galactic history or a pile of dust that dissolves into the wind.
The transition from passive observation to active interception marks the dawn of a new age in astrophysics, one where we stop treating interstellar objects as ghosts and start treating them as targets. 3I Atlas has proven that these visitors are not rare, once-in-a-century anomalies, but regular traffic through our solar system, and this realization has kick-started the engineering race to catch one. The challenge is velocity. 3I Atlas is exiting our system at a speed that makes our fastest chemical rockets look like they are standing still. To chase down a hyperbolic object, we cannot simply launch a probe and hope to catch up. The physics of a stern chase are brutal, requiring a change in velocity, or delta V, that exceeds the energy density of chemical fuel. This has led mission architects to propose the Solar Oberth maneuver, a daring concept where a spacecraft would not launch towards the target, but towards the sun. By diving deep into the sun's gravity well, effectively grazing the solar atmosphere, and firing its engines at the moment of closest approach and maximum velocity, the probe can leverage the Oberth effect to gain a kinetic energy multiplier that flings it out of the solar system at hundreds of kilometers per second. Current mission concepts like Project Lyra are using the data from 3I Atlas to model the thermal shielding and radiation hardening required for such a maneuver. We are learning that the interceptor must be more than just a camera. It must be a fortress, capable of surviving the solar hellfire before pivoting to hunt down a frozen rock in the interstellar dark. The analysis of 3I Atlas's dust hazard, the density of particles in its coma, is writing the safety manual for these future probes, telling us how much armor they need to survive a flyby at relative speeds where a single grain of sand hits with the force of a grenade. This is not science fiction. It is the immediate roadmap for the next 20 years of space exploration, moving us from the era of the telescope to the era of the starship. But before we can intercept them,
We must find them faster, and this is where the observational landscape is about to undergo a revolution with the activation of the Vera C. Rubin Observatory and its Legacy Survey of Space and Time, or LSST. For decades, astronomy has been like looking at the sky through a soda straw. We could see very deep, but only a tiny sliver at a time, which is why objects like Oumuamua snuck up on us. The Rubin Observatory changes the game by combining a massive aperture with an enormous field of view, creating a fire hose of data that will image the entire visible southern sky every few nights. The étendue, the grasp of the telescope, is so high that statistical models predict the detection rate of interstellar objects will jump from one every few years to potentially one every month. We are about to go from a sample size of 3, Oumuamua, Borisov, and Atlas, to a catalog of
hundreds. This flood of data will allow us to move beyond the study of individual anomalies and begin mapping the interstellar reservoir. We will be able to see if there are families of objects, clusters of debris ejected from specific star formation events in the galaxy's history. We will be able to correlate the chemistry of these visitors with the spectral signatures of nearby stars, perhaps even tracing a specific comet back to its parent system. 3I Atlas is the vanguard of this coming fleet, the final warning that we need to have our systems ready to process a complexity of data we have never seen before. Ultimately, the study of 3I Atlas forces us to confront the cosmic archive, the realization that the Milky Way is a giant, mixing ecosystem where material is constantly exchanged between stars. This has profound implications for the theory of panspermia, the idea that the chemical ingredients for life, or perhaps life itself, can be transported between worlds. If 3I Atlas is carrying complex organic molecules protected deep within a porous, icy crust, it serves as a proof of concept for the galactic distribution of biological potential. It suggests that Earth is not a biological island, but a port of call in a vast archipelago. Every impact of an interstellar comet on a primordial world is a potential seeding event, a delivery of the raw materials required to jumpstart the chemistry of life. By analyzing the outgassing of 3I Atlas this week, by watching how its organic rich crust reacts to the violence of the coronal mass ejection, we are testing the viability of this delivery system. Does the material survive the heat? Does the radiation sterilize it? Or does the comet act as a protective arc, preserving its cargo for billions of years across the void? These are the questions that lift the study of 3I Atlas out of the realm of rock mechanics and into the realm of existential philosophy. We are looking for our own reflection in the ice of a stranger. As we stand on the precipice of the NASA data release and the solar impact, we must recognize that this is a watershed moment. The silence is breaking, the sun is firing, and the data is flowing. We are no longer passive observers of a static universe. We are active participants in a dynamic, violent, and interconnected galaxy. Whether 3I Atlas reveals itself to be a fluffy ball of dust or a solid shard of diamond-hard ice, it has already succeeded in changing us. It has forced us to look up, to upgrade our eyes, to sharpen our theories, and to prepare for the day when we will not just watch the visitor pass, but reach out and catch it. The interstellar era has begun, and 3I Atlas is our guide into the unknown. To finally close the book on this deep dive, we must zoom out from the specific mechanics of 3I Atlas, the orbital eccentricity, the plasma tails, the solar collision, and confront the staggering philosophical reality that this object forces upon us. 3I Atlas is not just a rock. It is a physical confirmation of the cosmic archive, the grand and chaotic library of matter that binds the galaxy together. For centuries, we have viewed our solar system as a hermetically sealed bubble, an island of order in a vacuum of nothingness. We believed that our water, our carbon, and the very building blocks of life were local products, forged in the unique history of our own sun. But the presence of 3I Atlas and the realization that billions of such objects are drifting through the void at any given moment shatters that isolationist illusion. It proves that the Milky Way is not a collection of lonely stars, but a churning, mixing ecosystem where materials are constantly swapped, shared, and stolen between systems. This realization breathes new life into the hypothesis of panspermia, the idea that the biological potential of the universe is not static but mobile. If 3I Atlas is indeed a volatile rich body, protecting a core of complex organic molecules beneath a radiation-hardened crust, then it is a viable seed pod. It demonstrates that the precursors to life, and perhaps life itself, can survive the freezing billion-year journey across the interstellar gulf. Every time a star system forms, it ejects trillions of these seeds. Every time a giant planet migrates, it scatters them into the dark. 3I Atlas suggests that Earth is not a biological miracle in a sterile universe, but rather a port of call in a vast, interconnected archipelago of life. We are breathing air and drinking water that may have been topped off by comets from other stars eons ago, and now we are watching a fresh delivery sail past our window. As we prepare to watch the NASA live stream this Wednesday and monitor the violent impact of the coronal mass ejection on November 22nd, we are doing more than just gathering data points. We are witnessing the end of our cosmic childhood. We are transitioning from a species that looks up in fear and wonder to a species that looks out with intent and understanding. The silence that preceded this data release was the quiet before the paradigm shift. The noise of the solar storm is the drumbeat of our new reality. We are no longer alone in the dark. The dark is full of neighbors, full of history, and full of future targets. The legacy of 3I Atlas will not be defined by its specific diameter or its rotation rate, but by the change it has triggered in us. It has forced us to build the Vera Rubin Observatory to see the swarm. It has forced us to design Project Lyra to catch the ships, and it has forced us to admit that the sky is not a painting to be admired, but an ocean to be sailed. This is the interstellar awakening. The visitor has spoken, the sun has answered, and now, finally, humanity is listening. This is Axiox, signing off. Keep your eyes on the data, keep your eyes on the sun, and as always, keep looking up.